So we want to find h in A. If h q here, we have returned the position I. Because the start index is 1, so if it is not belong to A, we return 0. We want to find a recursive. Let ls A is the second h, the element we want to find, and R, the right and the end of the subsequent. At the beginning, we call ls A, h, and n. We want to find h in the whole sequence. So the right index in the first case is n. So we want to find a definition recursively. We split 3 cases. In the first call, we start from the 1 to n. We do a comparison here. If this element is not s, we restrict the search from 1 to n minus 1. And if here is not it, we continue to restrict the search n minus 2 and etc. If in the recursion we found down the h position R, we stop the search here, and the result in here is R. But if not, and we have here just one element. If in here is not the unique element, so the search go to the empty sequence. This here R is 0. This is the base case of the recursion. So if R is 0, we return 0. Yeah. In the case R is 0, we do a comparison. H is the element of the index R. So for example here, we return the index R. If not, we restrict the search to the linear search A, H, and R minus 1. We have a QC linear search increaser. We want to find the complexity in the worst case. We want to count the maximum comparison. So the complexity of n plus 1 comparison. The linear search algorithm recursive is simple but not efficient. So here we consider the binary search recursive. We set here L, R. The subsequent, we want to find the H, B, S, A, L, R, H. So in the first case, we call B, S, A, 1, N. Here we take the middle. The middle is left plus R divided 2. Do a comparison H with the element here. If H is greater than AM, we restrict the search to the subsequent from M plus 1 to R. If here H is less than, we have to search in the subsequent here from L to M minus 1. So in the base case, we make the empty sequence. We do not find out the H because the sequence in increasing order. So we write the definition. If the sequence is empty, the result of the search is 0. H not belong to A. Here, left is greater than R. In the other hand, we do a comparison H. AM for M is left plus R divided 2. Here we return the position M. But if H is less than AM, we restrict the search to binary search A, L, M minus 1 H. If H is greater than AM, we reduce the search M plus 1 and right. In the worst case, so here from the left to the right, the length is N. So it's N divided 2. And here maybe the right half N divided 4. So in the last, we just have one element. So one element will N divided 2 power of logarithm 2 N. We can express here N divided 2 power of 3. Here 2 power of 2. 2 power 1 to power 0. We can see here, this is the step 0, step 1, 2, the step of logarithm 2 of N. So the number of comparison is logarithm of n. So we can conclude complexity of the binary search is O log to n. So binary search is more efficient than linear search. So here we consider the sort by the merge recursively. In the first, we split the second into two halves. We split here. So continue. We split here. You see in the base. So we have here the increase second and the second increase second. And here we try to merge. We merge A and 2, and we have the list of increase in order 2A. We have to merge 2A and 4, so we have the increase in order here. In similar way, we merge 2 parts here. We also have here. Then in the last step, we merge the first one and the second one to the second in increasing order. So I can describe the merge here. We need two index. The run I change. We compare 1 and 2 because 1 is less than 2. So we have here 1. We increase child to here. Because the 2 is smaller, and we turn the index I to this element. So in here we have 2. In here we compare 4 with 3 because 3 is smaller than. So here we have 3. We turn here, check. We get here and maybe we turn here. We get some here and get some here, and maybe we can get and we turn get some here. So we have the sorted sequence. So now I want to demo the merge sort by a program in Java. We want to merge sort the array here. Here, for example, we can see here the code. So if left right we return, we compute the middle, the first half from left to mid, and the second half from the mid plus 1 to right. So we want to sort the first part, and then we sort the second part. Because the process in here is the same, the progress in here. So here we do the merge sort from left to mid, and here we have the merge sort from m plus 1 to r. So we call a recursion here. After we finish 2 recursion here, we have the first E increase in order, the 2 subsequent in increase in order. The last, we have to merge 2 parts into the result. So this is the code for merge. You can run here. So we have the result is increase and second. So I think the complexity of the merge sort is O and low rate up to n. Because the number we can cite here and the number we can cite here and. So we have n plus n plus n. The number step here is logarithm of n. And the number of comparison is n logarithm of n. The bubble of insertion is O n square.